What's up, physics? Welcome back to the dirt bike shed. We're going to take this car for a ride today. Now, we've been talking about centripetal acceleration, and we've been talking about centripetal force just a little bit. Well, let's talk about why this car can go in a circle. Right? Why can this thing go in a circle? Well, it's the tires, and the tires are touching the ground. Let's zoom in on it real quick. Now, for the car to go straight, not too much has to happen, right? But when we're going to turn, we turn the wheel has to make contact with the road, okay? And that contact with the road causes friction. And these wheels have a lot of friction, which is good because this car used to be fast before the transmission was messed up. And there's a lot of things that help this car friction. One, the tires are soft rubber, right? Tires are soft rubber. Now, why is this car sticking to the ground right now? Well, it's gravity, right? The acceleration due to gravity is going straight down on this car. And what is that number? Well, you know what that number is. It's 9.8 meters per second per second. So, if these tires had a frictional coefficient of 1, of the number 1, if these tires had a frictional coefficient of 1, then this car could go around a turn with an acceleration of 9.8 meters per second. What? This car can make some pretty good circles. And you see it's going pretty quick, right? Well, it could do a circle with an acceleration of 9.8 meters per second if the tires had a mu of 1, or if their frictional coefficient was 1. What would happen if the car tried to go around a turn with an acceleration higher than 9.8? Well, the car would slide out and it would go straight. I can make this car slide out going in reverse. Let's give it a shot. See, it couldn't do its circle. That wasn't very impressive. I think I got out of screen there. Let's try it again. You can hear the transmission shot. Let's try it. Ready? Look out, son. Here we go. See, the car couldn't do it because the frictional coefficient wasn't high enough. It slides out. Now, there's a video I like to show where they're trying to drive a really, really fast sports car around an ice rink. And you can see they're not very successful. The reason is the car slides out. And it's sliding out because it doesn't have any friction. It doesn't matter how powerful the engine is. Nothing. If we don't have friction, we have nothing. So the car just keeps trying to go straight. That's because the coefficient of friction is so low, and the ice skater outruns him around the track. It's the same thing with trying to go straight. Here's a guy who loves to buy new tires. Now, his tires are spinning, so he's not going forward very quickly. You need to have traction to accelerate in any direction. Traction is your coefficient of friction. If you don't have traction, you can't go around a turn. You can't go straight. You can do nothing. So let's go back. Let's go back to our green remote control car that we started class with, right? That I started the video with. Here it is. It's a view from the top. That's why it just looks like a rectangle. And we've got the tires here. Okay, we got the tires. They have a pretty good coefficient of friction. And if those tires had a coefficient of friction of 1, then we could go around this turn with an acceleration of 9.8 meters per second per second. In other words, if you have a mu equal to 1, then you can equal gravity at a 1-to-1 ratio, okay? These tires are probably have a mu of about 0.91 if I had to guess. So they're only going to be able to go around this turn with an acceleration equal to 9.8 meters per second times 0.91. The best they can do is 91% of gravity. So if I use my calculator, I'll say 9.8 times 0.91, and they'll be able to round this curve with an acceleration of 8.9 meters per second. That's the best it could do. Now, let's say we're going around a 1.5 meter, okay, 1.5 meter radius curve, and that's about equal to the beginning of the video. If we're going around a 1.5 meter radius curve, and our best acceleration is 8.9 meters per second, what maximum speed could we reach? Okay, AC equals V squared over R, right? Now the A is really only 9.8 times 0.91, because we can only do 91% of gravity, equals V squared over, we said the radius was of that circle was 1.5 meters, and that's about right. Then what velocity? What's the maximum velocity this little RC car can do before it slides out and goes off on a tangent, right? So 9.8 times 0.91, we said previously that that is 8.9. I'm going to switch colors so you can see that I'm solving. Is equal to V squared over 1.5. So now we're going to have 1.5 times 8.9. And then that's going to be equal to V squared. And I think you know what we're going to need to do to get rid of this squared is square root that. So I'm going to say 8.9 times 1.5 equals square root. That gives me 3.66 meters per second as the maximum velocity. Okay, 3.66 meters per second is the maximum velocity. Let's try another one. Now we're going to try somebody with a much lower coefficient of friction. Here's our red sports car driving around the ice rink. You can see he's spinning out. He's having a very, very tough time. Now, let's think about the turn here at the end. The turn he's going to try to go around. Let me come up with a radius for this turn, because you can see the skater, he's got a very high coefficient of friction. He's got skates that dig into the ice. But the guy driving the car is a very low coefficient of friction. I'm going to say that his tires have a very low mu. We're going to say that his tires have a mu equal to about 1/10 of what they should do. So we'll call that 0.11. There we go. He's got 11% of gravity that he can do. His mu is about 0.11. And if we're going around this ice rink, the turn at the end of the ice rink, let me make a guess as to what that turn. That turn is probably... the radius of that turn, I'm going to say, is about 8 meters, okay? Probably an 8-meter radius, and that's just a guess. And this is also a guess here, but let's think about the maximum speed that he's going to be able to go around this turn, all right? AC equals V squared over R, okay? So his maximum acceleration is going to be 9.8, because that's gravity. And he's only going to be able to do 11% of that, equals V squared over R, and the R is 8 meters. Once again, we're going to solve this. I'll switch colors to solve. 8 times 9.8 times 0.11. Get rid of the squared here. Square root That's going to be his maximum velocity. That gives us 2.9 meters per second. And I'm going to say that's a pretty decent guess. The fastest he could go around that turn is 2.9 meters per second. Now, let's think of something else that we need to take into account. What is the maximum force, okay, that the tires, here's the tires, right? Here's our little car, here's the tires. What's the maximum force that these tires can push the car with? Remember, they're pushing the car to the inside of the turn. That's why tires get worn out. That's why they get bald. What is the maximum centripetal force that these tires are going to apply? All right? Well, we would have to know something else. What else do we need to know force? We need to know how much that car, what its mass was. I almost said how much that car weighed, but really we need to know what the mass of that car was. And that's a Jaguar, so it's not too awful heavy. I'm going to say it's about, I'm making a guess here, 1,200 kilograms. All right, got a 1,200 kilogram car. So the maximum centripetal force is mv squared over r, right? And what is force equal to, right? Force is equal to mass times acceleration. So we can super simplify this problem. What is this part of the formula right here? Boop, boop. That is acceleration, right? It is. This is really just F equals ma, except for the a is the centripetal acceleration. What's the best acceleration we can get around this turn? The best acceleration is going to be 9.8 times the mu of the tires, 0.11. So if we want to find the centripetal force, it's F equals ma. What is the mass of this car? 1,200. So 1,200 times 9.8 times 0.11. Even though that car is very heavy, the tires are only going to be able to apply 129 newtons of force to keep the car pointed towards the inside of the turn. Once that force is overcome, then the car will travel on a tangent and keep going straight, right? It will keep going straight at any time when more than 129 newtons of force is required. Okay, we're going to work one more. All right, you want to copy this problem, and I'll read it to you. What is the maximum acceleration, velocity, and force that can be applied to a 900 kilogram car rounding a 30-meter radius turn if the tires have a mu of 0.87? Now, the thing about this problem is it's realistic, okay? This 0.87, according to the tire manufacturer Dunlop, is good traction. If you have new tires and you're driving on a dry road and you have an average car, then your coefficient of friction is 0.87. This 30-meter radius turn is a turn you might see on the road. It's a fairly sharp turn. It's sharper than you would think it would be. A 900 kilogram car would be about the correct weight for a small car like a Kia Soul or something like that. So right now you can pause the video and try to solve this problem yourself. And if not, just keep watching and I'm going to solve it. All right, here we go. First thing I'm going to do, I'm going to draw a picture. Okay, it doesn't matter what direction you're going. I'm going to go this direction this time. All right, boom, I got a car. We have a radius. The radius to our turn is 30 meters. Okay, that's about 100 feet or so. So that's a pretty tight turn. All right, here is our car. All right, I'm going to draw it from the side this time, just there's a little Kia Soul. Okay, I used to have one of those. And it's trying to go around this turn. Its tires have a coefficient of friction of 0.87. So the first, and it weighs 900 kilograms. So, first things first, let's figure out the maximum acceleration. The max acceleration is going to be very simple to find. First thing you do say, all right, gravity, that's what holds us to the road, and we're only going to be getting 87% of that. So our max acceleration is 9.8 times 0.87. Excuse me, yeah, times 0.87. So the acceleration is going to be 8.5. I'm keeping my numbers simple. 8.5 meters per second. That's the best acceleration we can do. Now, logically, let's find that velocity. AC equals v squared over r. Very simple. Our maximum acceleration is going to be 8.5 meters per second. We're looking for the velocity around a turn that is 30 meters, okay? So 8.5 is equal to v squared over 30. 30 times 8.5 square root will give us that v, right? I'm doing algebra 1 here. You're like, Mr. Perkins, you're going too fast. I am not. I'm doing some 8th grade algebra 1. 30 times 8.5 equals square root 15.96, or we're just going to call it 16 meters per second, is the best velocity you can do. And that's not miles per hour. 16 meters per second is pretty quick. It's like 40 miles an hour. I think. I'm making a guess there. All right, so 16 meters per second is the maximum velocity that you're going to get over here. If you go faster than that, whoop, you're going to slide out and go straight. Okay? Last question. The last question was, what is the maximum force that these tires are applying to the road? So the tires are gripping the road, and like I said, that's why they get worn out. That's why your tires go bald. They're applying a force to the center of this circle constantly, and that force has to do with how heavy the car is. A heavier car will wear out its tires faster, and how fast you're going. Very, very, very simply, don't forget Newton's second law, F equals ma, and we can just throw little c's on there, and that means we're going in a circle. The mass of the car is 900 kilograms. And what did we just say the acceleration was? The best acceleration? We just said the best acceleration that we could get. See, this is our m. We just said the best acceleration that we can get is going to be 9.8 times 0.87, right? So that number is 8.5. So it's painfully obvious now that F equals ma means 900 kilograms times 8.5 meters per second, and that's going to come out to be 7,673 newtons. 7,673 newtons, okay? There you go. I am going to give you a simple assignment with some simple problems, and thanks for sticking around.